Good morning. Let's start our lecture. Today we are going to continue our discussion on simple harmonic motion. Right? In the previous lecture, we already have discussed about the equation of motion of a simple harmonic motion, and we also have solved it with two undetermined constant that is to be fixed by the initial condition, and we also have discussed about how to match the initial condition. Given arbitrary position and the velocity, initial position and the velocity of the object, we can write down the general solution for that problem. That's what we have discussed in the last lecture. Now, now we extend our discussion a little bit. In the last lecture, we neglect gravity. We suppose the oscillation to be in the horizontal direction, so gravity can be neglected. But now we want to include gravity also in the consideration. We want to hang a mass by using a spring in a vertical position, such that the mass is subjected to the force of gravity and also the force of the spring. So let's see how this would modify the equation of motion, and how can we solve it. Now, so we discussed about SHM with a constant external force. The constant external force is, of course, gravity. Okay. Now, so this is the situation now. The mass is subjected to a gravity force of mg, which is, of course, its weight, and it's also subjected to a force due to the spring, which is in this figure is in upward direction. Now, so consider now the mass is at rest. Now, this level indicated by a blue line is the unstretched position of the spring. So when the mass is at this position, the spring is unstretched. So the force due to the spring is 0. Okay, when the mass is at this level. Okay, so this is unstretched position. This is the position which we call x equal to 0, the extension equal to 0. But now, since the mass is acted by gravity, it has a weight, right? So there will be extension because the weights stretch the spring, right? So there will be extension, and I call this extension x0. Now, at this position, the mass is at rest. Okay, so it is in equilibrium. So the force of gravity just balances the force due to the spring. And I suppose that at this equilibrium position, the new equilibrium position now, we have extension x0. So the weights of the mass is balanced by the spring, the force on the spring, which is kx0. Okay, because the spring now extend an amount of x0. So this is the kx0 is the force on the spring, which balance the weights of the mass. So I solve for x0. x0 is equal to mg over k. Okay. Now I stretch the mass further down, such that its general extension is x. Okay. And so I want to describe its subsequent motion when the mass is being released. Okay. When the mass is at the general distance x below this level, then I would like to write down the general equation of motion. Okay. Now the force of gravity is still there, so I have downward force of gravity mg, and I take the downward direction as positive now. So the mg is positive. The force on the spring is in the upward direction, right? So it's minus kx. Okay. X is a general displacement from the unstretched position. Okay, so the general force due to the spring is minus kx if the general displacement is x. Okay, so the total force, the net force, is equal to the mass times the acceleration. This is Newton's second law. Okay, so we have the differential equation now. Now you should note that this differential equation is not much different from the SHM equation that we have solved. We only have got an additional term. That additional term is actually a constant term mg. So apart from this term, the equation is very similar to what what we have solved before. It's identical actually, if without this term. Now we divide the whole equation with the mass m, and this becomes g, the constant acceleration, and this term is the same as before, minus k over mx. So we can rewrite the equation as for the follows. Now, how do we solve this equation of motion if there's a constant g? Okay. Now, the trick is like this. The trick is like this. Instead of making reference to this level, which is called x equal to 0, we now make a change of variable. The change of variable is to cat c, a new variable cat c. So what is the relationship between cat c and x? Now, cat c is very simple. At the equilibrium position of the mass under gravity, I call this level cat c equal to 0. Do you understand? So cat c equal to 0 is actually the equilibrium position of the hanging mass. It is not the position of unstretched spring, but the equilibrium position of the hanging mass. Okay, it is the level at which the mass is placed, such that the gravity force just balance the force on the spring. Okay, now so the two level, you see the two level are just different by a constant x0. So that if I have a general displacement like this, if I measure it from the unstretched position of spring, I have x. If I measure it from the equilibrium position of the mass, I have cat c. The two variables are just different by a constant amount of x0. So I can define cat c like this. Cat c is equal to x minus x0. The two variable x or cat c, they are just different by a fixed amount, and that fixed amount is cat c x0. Okay, so cat c is equal to x minus x0 is equal to x minus mg over k. This is the x0 we found, right? Now, so the second derivative is the same. The second derivative x and second derivative of cat c actually the same, because the two variables are just different by a constant. Okay, but this term help us because when we transform this x on the right hand side to cat c, instead of writing the equation in terms of x, I now write in terms of cat c. In terms of cat c, the x become x cat c plus mg over k. I move this term to the left. Okay, so I replace the x by cat c plus mg over k. Now you realize that after canceling the m and k here, this constant term gives you a minus g, which cancel with the constant term g at the end of the equation. Okay, so these two terms actually cancel, and I got the term, only the term minus km over cat c without the constant term. So by shifting the origin, I get rid of the constant term. Okay, this constant term eventually cancel if I express everything in terms of the new variable. So in terms of the new variable cat c, the equation is completely simple harmonic. Okay, and I can actually solve the equation with the method that I outlined before in the last lesson. The whole method will work, and I don't have to repeat it. I just write down the solution. Cat c can be written as a cosine omega naught t plus phi. Omega naught is the same, it's k over m square root. It doesn't change. You have the constant a and phi for the initial conditions. And then x, if you insist of expressing the result in terms of x, then you just add the constant term mg over k. Okay, you just add it to cat c and everything works. Okay, so it's just a shift in equilibrium position. There's no change in frequency. Now, if you stretch the spring and release it, the mass just oscillate about the new level of equilibrium, about cat c equal to 0. It oscillates up and down about this level, but not about the unstretched position of the spring. Okay, so that is a physics inside. Any question at this point? Now, if not, then we would discuss an interesting topic on generality of simple harmonic motion. What is called generality? Generality means something very general. Okay, it means that the harmonic, simple harmonic motion, that kind of oscillation, can actually be applied to a wide range of problems in physics. Those wide range of problems ranging from oscillation of electromagnetic cavity, EM waves, the mass spring system, or even atomic lattice in a crystal, the atom vibrates inside a crystal. They all can be described in terms of simple harmonic motion to a certain extent. Okay, so we would try to understand heuristically why this is possible. Why this is possible? Why the simple harmonic motion method is so powerful that it can be applied to so many different method, different regime. Okay. Now, to make things general, let us go back to general potential energy curve. In chapter 5, we learned about the different kinds of equilibrium, right? We plot the potential energy against the position. So we have a graph of U versus X. And if you recall chapter 5, you remember there are two kinds of equilibrium that we have mentioned. The first kind of equilibrium is called stable equilibrium. Is that the potential energy curve has a minimum, okay? And the second kind is a unstable equilibrium in which the potential energy curve has a maximum. Now, when the potential energy curve of has a minimum, then the equilibrium is stable. Why? Because at this point, I know that the force acting on the particle is 0. So this is an equilibrium, right? du dx is equal, with a minus sign, is equal to the force. And du dx here is 0 because the curve is level. So this is a 0 point for the force. But how about what determines what is stable or not? Depends on what happens when the particle is slightly disturbed. Suppose the particle is slightly disturbed from equilibrium. Suppose the particle is now moved to the positive x side by a little bit. Okay. Now you see the slope du dx is positive, but you have a minus sign. Minus du dx is a force. So the force will become negative, and that will move, and that will tend to move the particle back to this equilibrium position, right? So you disturb it to the right, and the force move it back. And similarly, if you move the particle to the negative x direction by a little bit, the force will be in the positive x direction, and it tries to move the particle back to the equilibrium position. So that's why the point it will be stable. A slight disturbance will not disrupt the equilibrium, but the force, the conservative force, will tend to move the particle back to this equilibrium position. That is what we mean by stable equilibrium. Now we want to show that when there's a stable equilibrium, whenever there's a stable equilibrium in the potential energy curve, then a slight disturbance from that equilibrium will displace the particle slightly. The particle will oscillate back and forth about that equilibrium in a simple harmonic oscillation. Now this holds as long as the oscillation amplitude is not large, is small enough. Okay, that is the only condition. Now we would like to have the general proof on that. Do you remember the Taylor series expansion? That's why we learn a lot of approximation, because the approximation is actually very important in physics. Now we expand the potential energy, the shape of the potential energy curve about the equilibrium position as a series, Taylor series. So Ux can be approximated by what? The first term is Ux naught, the value of U at the equilibrium position. The second term is the derivative of U at x naught, again, multiplied by x minus x naught, right? And the third term involves the second derivative of U at the point x naught. Okay, so it's 1/2 U double prime x naught, x minus x naught square. And of course, you have the higher order term. But for a displacement small enough, if x minus x naught is small, that is the displacement is small from the equilibrium position, the higher order term is negligible, and they are all negligible. So it is sufficient to make an approximation on u up to the second order term, which is x by x naught squared. Okay, we neglect the higher order, the third order, the fourth order, they are not important. Okay, because the displacement is small. Okay. Now, but we notice that the second term is 0 because this is equilibrium, and the force is given by minus du dx, right? But du dx at the equilibrium position is of course 0. This is a minimum in the potential energy. Okay, so we don't have this term. What we have is the constant term plus the second order term that goes as dx minus x naught squared. Okay. Now we are going to derive the force. If you remember, if you are given the potential energy, you can derive the force from its derivative, if spatial derivative, with a minus sign. Okay, so I differentiate this with respect to x, adding a minus sign, I get the force. The constant term doesn't matter because the differentiation of it is 0. This term, if I differentiate it, I got 2x minus x naught. That is the all, right? So the 2 cancel with this 1/2, and I got the force as minus u double prime x minus x naught. Okay. Now, so the equation of motion become what? The major equation of motion become the net force equal to ma m dx squared d squared x dt squared, right? Now we do the same trick as before, right? Because there's a constant term x naught. Okay. Now you see this guy is already very similar to the what? To the simple harmonic motion, except for this constant term. But we have learned how to deal with this, right? A simple change of origin to the position of the origin will get rid of this term. We just have did that in the previous example, right? So we know how to do that. Now this u double prime is actually a constant because it is the second derivative of u evaluate at the equilibrium position, which is a constant. It depends on the shape of the curve at the minimum of u, at the minimum point of u. So this is actually a constant. Okay, so the force is a constant, a negative constant, multiplied by x minus x naught, which is of course a simple harmonic motion. Okay, now we change a variable. We don't want this constant x naught, so we change a variable from x to x minus x naught. So we just substitute cos c into this term. Okay, for this term. So now the right hand side becomes cos c, and the left hand side, because cos c and x they just differ by a constant. So the second derivative they are just the same. Okay, so the dx the second derivative of x is just the second derivative of cos c. So we now write the equation totally in terms of cos c, and obviously because this guy is a constant, and so we recognize that this is a simple harmonic motion. Okay, and what is the frequency for this? Now the frequency for simple harmonic motion can always be obtained from the coefficient before the displacement. The coefficient before the displacement is actually the square of the frequency. The standard equation for simple harmonic motion is acceleration equal to minus the frequency square that is multiplied by the displacement. Okay, now I write there. This is the standard, sorry. Remember this, right? So this guy actually is the omega naught square. Okay, Now, whenever you see an equation of this form, you can conclude that the equation is simple harmonic. Okay, so this omega naught now corresponding to square root of this guy. So the frequency is actually square root u double prime x naught over m. And the general solution, we don't have to do everything again, right? Because we know that this is simple harmonic anyway. Okay, so we just write down the solution. And if you want to express everything in terms of x, just add the x naught, just add a constant x naught to it to get C. Okay. Now, so you may wonder, what have we done actually? You expanded in Taylor series and you got a simple harmonic equation of motion, and then you got the frequency. So what actually have we done in this process? Now I can explain it to you simply by using a picture. Now look at the potential energy curve. In general, the potential energy curve may be complicated, right? It may be rising up and down in a very complicated way, and it may not be symmetric. For example, this side may be flatter and this side may be steeper. We don't know its actual shape. So the blue curve here in this graph actually represent the real U. Okay, this is a real potential energy. But what we have done is that we want to approximate the potential energy curve by the red curve, which is a quadratic equation. The quadratic equation goes as a constant term plus a term that is proportional to x minus x naught square. Okay, so you can see this is actually a quadratic parabola, right? A parabola, and the minimum of the parabola is of course as x equal to x naught, where this term vanish. Okay, so you now have a quadratic curve, which is the parabola, which is like this, with a minimum in the same position as the original U curve. Okay, the two curves actually have the same minimum. Okay, so this is the idea. Now, what is K, right? We choose K in such a way to match the second derivative of the U, the curvature of U, of the real U at the minimum position. So K is actually U double prime at x naught. So by choosing K to be U double prime at x naught, the two curves actually become very close to each other in the vicinity of the equilibrium position. So I can now use the red curve, the red dashed curve, to approximate the green, the blue curve when I'm getting very close to the equilibrium position. So that is the meaning of this. Okay, my K is just U double prime x naught. Now, but you see, the approximation may not be good if I move farther away, right? If you move farther away, then the two curves, the discrepancy between the two curves might be large. But you should know my condition. My condition is that as long as I maintain a small amplitude oscillation, the simple harmonic approximation is valid. Okay, as long as I'm considering an oscillation which is very close to this point, the difference between the two curves is not important. So I can ignore the high order term, the x minus x cubed, x fourth, I can ignore them all. Okay, that is the meaning of it. Okay, so we can approximate every oscillation whenever I have a U like this with a spring mass system that obeys Hooke's law, essentially, right? Just by replacing the spring constant K by the second derivative of the actual U function. That is the idea. Now let's have a very simple example. It sounds abstract, right? But so let's get a simple example. Suppose in some region in space, the potential energy is given by this function. Now look at this function. When x is getting close to 0, the exponential term is 1, right? Exponential minus k, 0 is 1, right? So it's dominated by minus x. So the curve begins with a minus x, which is a straight line downwards, right? Minus, this is the U equal to minus x, right? But when x is getting large, you see the exponential term will dominate over. And exponential term always tends to 0. So eventually the curve will tend to 0, but from the negative side. Okay, so when x is large, this guy will eventually go to 0, but never touch that's the x-axis. Okay, so initially goes downwards and eventually goes to tends to 0. So there must be a minimum point in between. So this minimum point is the minimum point for the potential energy, and that is a stable equilibrium position. And we want to find an oscillation as a simple harmonic motion about this equilibrium position. And we want to find that oscillation frequency about this position. Okay, so let's do it. Now let's take the derivative of u. Now I don't bother with the mathematical details. I think with this simple function, you can handle the differentiation yourself. So I differentiate this. I use the product rule. I differentiate x first, and then I differentiate the exponential term, and I sum up the two, and I got this value, kx minus 1 exponential minus kx. Now I noticed that u prime is actually 0 when kx minus 1 is 0. And that exactly corresponds to this point, the minimum point. The minimum point has a 0 first derivative of u. Okay, so u prime is 0 when at this point where x equal to x naught is equal to 1 over k. So okay, that is the equilibrium position. And I then proceed to find the second derivative. I differentiate this guy again. I differentiate the brackets where I call x plus by the product rule, I keep this term intact, and then I differentiate the exponential term again, which I got a factor of minus k. So simple algebra will lead me to this guy. Okay, so this is the second derivative of u. Now I evaluate the second derivative of u at the equilibrium position. The equilibrium position is x naught, which is 1 over k. Okay, I find it here. Okay, by putting this to be 0. So I just put this x equal to 1 over k. The exponential, the x in the exponential, I also put it 1 over k. So this 2 minus 1 is 1. And this is e to the power minus 1. So I got k e to the power minus 1. This is my second derivative. Okay. So by the equation of motion is this. I don't have to do it again. Okay. Because I know the answer already. Okay. That direction is general. For a general shape curve is okay. So I immediately got the frequency. The frequency is square root u double prime over m. And u double prime is this guy. So I just put it in and I got the answer. Okay. So it's not difficult. Okay. Any questions so far about this problem? Now, if not, then let discuss let me give you a example to illustrate why the simple harmonic approximation is so interesting and so important in physics. Now consider, I don't know if you have met this model before. This is called the van der Waals potential. If you consider two atoms or two molecules in a solid, okay, there will be an equilibrium distance between them. Okay, that the two atoms will not get too close, it will not get too far away. There will always be an equilibrium position at which the two atoms or the two molecules are located at rest. Okay, and that is called the equilibrium. Okay. Now, but you may understand why there's such an equilibrium. Why the two atoms or the two molecules cannot get too close, or they cannot get too separate too far. Now, because when you try to separate them, if you consider two molecules in a solid, That would be intermolecular force. The intermolecular force is sometimes called the van der Waals attraction or the van der Waals force. Now, it's actually due to the electric dipole of the atom. Now, I will not teach you electric dipole, actually. It is a slight separation of charges, the positive and negative charge inside the atom. I will teach you if you study year 2 physics on electromagnetism, but I'm not going to teach you now, okay? Imagine the atom consists of electron and the positive nucleus, the negative electron and positive nucleus, and sometimes the electron are just slightly separate from the positive charge nucleus. And so that results in an uneven distribution of charge, and that is a dipole. And the adjacent atom, if they have such a dipole moment, they will attract each other. And that results in an intermolecular force called the van der Waals force. But the van der Waals force, it dies down very rapidly. Then it is attractive, so the potential is negative. But it dies down very rapidly when the two molecules are separate, widely apart. The force decreases very rapidly with distance. And it turns out that it decreases with the distance to the power 6. Okay, so the distance dependent is 1 over r to the power 6. That is a high power. Okay, so it decreases very rapidly. But why can't the two atoms be getting too close together? Because the electron cloud, they repel each other. Okay, now the electron cloud, when the two atoms or the two molecules, when the two electron cloud on this outer layer, they tend to overlap. Okay, it is not the electrostatic force that repel them, but there's a new kind of force. This is called this is of quantum nature. Okay, it's a quantum kind of force. It is called the degeneracy force. The degeneracy force is due to the Pauli exclusion principle in quantum mechanics. The Pauli exclusion principle states that no two electrons can occupy the same energy state. So when you try to squeeze the two molecules together, the electron in the orbital in the quantum state, they will try to be squeezed to the same state. And Pauli exclusion principle simply tells you that they don't like that. They will exert a large force to oppose that. And that is called the degeneracy force in quantum mechanics. And the degeneracy force actually results in a very large repulsive force. And there's a very strong distance dependence of 1 over r to the power 12. So this is the potential is very strange. One term goes as r over to the power 12. The attractive terms goes as 1 to r to the power 6. So when the particle comes very close together, the Pauli term dominate, and so you have a strong repulsion here. The U become very large to infinity. Okay, when the two molecules are separate, wider apart, the attraction force will dominate because it dies down already. R to the power 12 dies down very rapidly. So when the two particles separate far away, the attractive terms will dominate. So it goes as minus 1 over r6. And in between, there's an equilibrium position. Okay, and the equilibrium position is given by the derivative of this u by putting this derivative of the derivative of the u to be 0. Okay, so I can solve for A. Okay. Now this equation is rather messy, so I will not give it to you as an exercise, but I can have a simplified model of it. Okay, in your homework, I will give you a simplified model of not so high dependent on power, but low dependent on power. So you can easily calculate. Okay. So even using classical mechanics, we can predict the oscillation frequency, the simple harmonic oscillation above this equilibrium position. So the two atoms actually vibrate about this equilibrium position. Okay. Then we would like to introduce a damping to the equation of motion. Now, if you observe the oscillation in our daily life, we can see that the oscillation will die down with time. It will not oscillate forever, because when the particle oscillate, there will always be energy dissipation. The dissipation may be due to friction, it may be due to air resistance, or a combination of the two. So eventually, if you see a spring mass system oscillating like this, the amplitude of oscillation will eventually decrease, and eventually the oscillation will die down. Okay, and that is called damping. That is called damping. So we want to now we want to obtain a simple model of the damping. Okay, by adding a term, a damping force, to the equation of motion, we can obtain a simple model of a damped harmonic oscillator. So that's what we want to do. Now, suppose besides the restoring force, which is typically the force of the spring, the particle is also subject to a viscous force. I think you already are very familiar with this equation. The viscous force, the viscosity is proportional to the velocity. So if you move with a larger velocity, you get a larger resistance, right? As in opposite direction to the velocity, so you get a minus sign here. The proportional constant is B. Now, to be fair, I would like to emphasize that this is a model only, and this model may not be accurate in some situation. The general resistive force may go at minus B V to the power n, where n is a positive number. Okay. Now we only choose the n equal to 1 case for the viscous force. And in fact, for the air resistance of a large body with high velocity, you have seen that the air resistance actually goes as V squared, but not V, right? We learned it in chapter 4, right? I think when we learned Newton's second law, we learned about the air resistance. It typically goes at V squared, but not V. So this model is not very accurate, actually. But the resulting equation is simple with this model. Because V only appear once in this equation, it's not V squared. So the resulting equation will be linear, and linear equation is always easy to solve. If I put V squared here or V to some power which is not 1, then the resulting equation will be a very complicated non-linear equation, which is obviously outside the scope of this course. So for this course, I will maintain a simple model. So I choose the BV model. Okay. Now, so this is the equation of motion. You just add this term. Okay. You just add the term BV as the net force, as a part of the net force. Okay. Of course, you still have the force on the spring. You are talking about a spring mass system. So we now divide the whole equation by m, and then we move all the term to one side. So that result in this equation. And similarly, similar to the simple harmonic motion, we define omega naught as k over m square root. So the constant that go in front of x is still omega naught square. This time it still remain the same. Okay, but we have a new term. The velocity can be written as dx dt, right? The first derivative of x is the velocity. And I can write a shorthand of the equation as B over m. I define it as alpha. Alpha is simply a shorthand for B over m, but it's nothing, okay? So this is a so-called linear second order differential equation with constant coefficient. And this equation has standard method to solve, okay? It is second order, okay? It goes at a term that goes to x. It has a term that goes at the first derivative of x, and you have a term that goes at second derivative of x. So that's why it's called second order equation. Okay, second order differential equation. And all the coefficient of x of the x dt of the second order of second derivative of x, all these coefficients are constant. Okay, so this equation is easy to solve. Now, but before solving this equation, now we can proceed solving in a straightforward manner. without further discussion. But the physicist, he's always expecting something from the solution. Before he do it, he will expect we got something from this equation intuitively, because he know what's happening, right? We know that usually that we describe a oscillation with an amplitude that is dying down, right? The amplitude will be decreasing. That is something we will expect. Okay. So at least for some oscillation, especially when the damping is weak, we expect that the oscillation has a decaying amplitude. The amplitude goes down, and the frequency may be affected by the damping. So that may be a change in frequency as well. Okay, so we have these two expectations and see how we can solve it. Why not make a guess? The guess is that the solution is given by an exponential function, e minus gamma t, multiplying by oscillatory function cosine omega 1t. Now, without this exponential term, without this e, the solution is very similar to simple harmonic motion. But now we have a decaying amplitude. The amplitude decay as an exponential function. We don't know how fast it's decay, so the coefficient before the t, it characterizes how fast the decay will happen. Okay, and I call this constant gamma. So I suppose a decay that goes as e to the power minus gamma t for the amplitude. Okay. As I say, the oscillation frequency may also be affected. So instead of just writing cosine omega naught t, where omega naught is the frequency with no damping, we now write the new frequency, which I call omega 1. So this omega 1 may be different from omega naught. Okay, so the oscillation is still there, but the oscillation happens in a different frequency, omega 1. So the product of these two terms will give you a decaying oscillation. The cosine term will be oscillating, but because the amplitude decreases, the oscillation will eventually die down. That is what we expect, right? And so let's see if this equation works. We are guided by physical intuition to propose such a solution. So let's hope for the best. If this solution is going to work, then when we substitute this solution into the equation will be satisfied, could be satisfied for all time t. Okay. Now, but we notice that we have introduced two new constants. The first constant is gamma, which characterizes the rate at which the amplitude decreases. The second constant is the frequency, the new frequency of oscillation, which we call omega 1. They are the new constant proposed by us. They are not existing in the equation of motion. So, but there must be a relation between the two. If this solution is going to satisfy this equation, then the coefficient in the differential equation must be related to these two constants. So alpha and omega naught must be somehow related to gamma and omega 1. There must be a relation between the two. So so our task is to show that this solution can satisfy this equation, and at the same time, we will find out the relationship between alpha omega naught and gamma omega 1. So that gamma omega 1 can be expressed solely in terms of alpha and omega naught. So we complete our solution. That is our task. Okay. Now, in my version of the PowerPoint, you already have this coefficient, but imagine you don't have it. Okay, I posted on the web. Of course, you have this answer, but imagine you don't have it. And I start with this solution, and I find the derivative of x, and I find the second derivative of x squared. I got the coefficient before the sine and the cosine. Now, so I'm going to give it to you before as an exercise before the break. We start with this solution. The product rule of differentiation implies the first derivative and the second derivative goes like this. Now, why do we expect this? Now, it's easy to see. When you differentiate x, you either apply by the product rule, you either apply the differentiation on the exponential or on the cosine or the sine term, right? When you apply it on the exponential, it just gives you back the exponential, okay? So when you apply it on the cosine term, you turn into a minus sign. If you applied it on a sine term, then it goes back to cosine. So no matter how many times you differentiate this guy, you always end up with expression of this form. It somehow must be contain terms that goes as a cosine or sine multiplied by an exponential factor. You always get this term. So to make this the calculation systematic, to reduce the chance of making error, let's write down our expectation. The general solution, dx dt and d square x dt square must look like this. Okay, a cosine term and a sine term, and then they go together and then multiply by the exponential. And you are going to calculate this coefficient. Okay, you do it systematically, and you calculate this 6 coefficient. Now for the first line, of course, the cosine term is 1. This is 1. The sine term is 0. We know that. But for dx dt and d square x dt square, you are going to do it. Okay. Now I check with you after break. Let's have a break for 10 minutes, maybe for 15 minutes, because you need time to do this, right? And you find out the coefficient. Okay, and I will check it with you after the break. Okay. If you have any questions, please ask now.